Hi everyone, welcome back to MATA35. Today we are going to be talking about matrix inverses and determinants. So these are some of the most important concepts in linear algebra, second only to eigenvalues and eigenvectors, which we're going to be talking about next week. But this will get us sort of set up in talking about how matrices behave. So now I remember in our lecture last time, someone mentioned the idea of dividing by a matrix. Now, what does this really mean? And like when we think about it, we have some operations that we all know and love. So for example, we have addition, and we know how to do lists. So this is just 1, 2, 3, 4 plus 2, 4, 6, 8. You just add each of the terms individually, and you get 3, 6, 9, 12. And if you have addition, you also have some idea, like you might also come up with the idea of subtraction. And I'm going to write this a little bit weirdly because really, when you think about it, subtraction is the opposite of addition. So you can think about starting from this 3, 6, 9, 12, and if you subtract one of these matrices, let's say 2, 4, 6, 8, then you want to get back the original 1, 2, 3, 4, right? Since you're doing the exact opposite operation, and so you get back 1, 2, 3, 4. And for subtraction, this is easy because you can just subtract each of the individual entries component-wise. But now, things get a little bit more complicated with multiplication and division. Multiplication with multiplication and division because, well, matrix multiplication is weird, right? So if we start with 1, 2, 3, 4, and we want to multiply it by 2, 4, 6, 8, that's going to end up being, well, this is 2 plus 12, because it's 1 times 2 and 2 plus 2 times 6, so we have those two pieces, and so on. So that's going to be 4 plus 16, and 6 plus 24, and 12 plus 32, using all the inner products. And that's going to be 14, 20, 30, and 44. Okay? So now, when we want to do division, what we want to do is we want to take the opposite operation. We want to take the inverse operation, which is a term we're going to hear a lot for multiplication. So what we want to do is we want to have some operation that allows us to start with the matrix 14, 20, 30, 44, and we want to have some division operator, which we haven't defined yet. So this is all stuff that doesn't exist yet. We want to somehow divide by 2, 4, 6, 8. And we want this to equal 1, 2, 3, 4. Now, one of the ways that we define the subtraction operator is we define it as just adding another matrix that we've converted. We've added a matrix that is the additive inverse because we've taken minus signs on each of the entries. Now, the problem is when we're doing division, we want to find some matrix where we can multiply by it and do the opposite of multiplication by the earlier matrix. It's a little bit hard, but let's think about exactly what this means. So again, let's go to the real numbers and think about what we mean here. So one way to think about division in real numbers is multiplication by an inverse. Let's give an example of that. So this is all basic grade school math. If you want 15 divided by 3, well, that's equal to 15 times the inverse of 3, well, 3 reciprocal, which is equal to 15 times 1/3, which is equal to 5. But now, can we do something similar for matrices? And now, I'm going to magic up a matrix, which I'm going to call the inverse of 2, 4, 6, 8. And we're going to talk about how we come up with these matrices later, but let's say we have 14, 20, 30, 44, and I'm going to multiply it by the matrix minus 1, 1/2, 3/4, and minus 1/4. Don't worry, I just pulled this matrix out of thin air, so don't be surprised if this doesn't make any sense yet. We'll talk about how to calculate this matrix later. But when we multiply this out, what we end up getting is minus 14 plus 15, because 20 times 3/4 is 15, and 7 minus 5, and we have a minus 30 plus 33 here, and 15 minus 11. And so it turns out that you do end up getting 1, 2, 3, 4. So somehow I was able to find this matrix, minus 1, 1/2, 3/4, minus 1/4, that when you multiply by it, seems to undo the operation of multiplying by 2, 4, 6, 8. Therefore, what you get is that minus 1, 1/2, 3/4, minus 1/4, we're going to call that, and we haven't defined this yet, but, well, let me take out this question mark. We're going to call that the inverse matrix of 2, 4, 6, 8. And we're going to use this notation to the minus 1 because that's basically the matrix that you multiply by to reverse the operation of multiplying by 2, 4, 6, 8. Okay, so now that we have this idea of an inverse operation, let's go back and look at some properties of these inverses and how things differ a little bit when you're talking about real numbers versus matrices. So if we have a multiplicative inverse, that is just the number you multiply by to simulate division, to undo the operation of multiplication. So it's some other real number. If you have a real number x, the multiplicative inverse is 1 over x, such that when you multiply x and x inverse, you get 1. And it doesn't matter which way you multiply because, well, multiplication is in the real numbers. It doesn't matter which order you do them in. So let's give a couple examples. So 1 inverse is just equal to 1. 2 inverse is equal to 1/2. Pi inverse is equal to 1 over pi. So this is all fairly straightforward. But let's give another special case. 0 inverse doesn't exist. This is not a number. And this is because it turns out that when you multiply by 0, there's nothing you can do to undo that multiplication. So now, and of course, we can use these numbers to reverse the multiplications, as we've been discussing. So if you take 1/2 of 2 times 3, that's reversing the operation of times 2. And the reason this works is because you can use the associative property, so that's 1/2 times 2 times 3, which is equal to 3. Or you can also think of this as 1/2 times 6 is equal to 3. But now, of course, for 0 doesn't work. So y dot times 0 is equal to 0 cannot be reversed. Okay, and so 0 doesn't have an inverse. And it turns out there will be some matrices that when you multiply by them, you can't reverse them. One obvious example would be the 0 matrix. But it turns out that when you have matrices, there are lots of matrices that you can't reverse. And so it's important to know when you have an inverse. Okay, so now let's generalize to matrices. So if we have a square matrix, and it turns out that we're only going to talk about multiplicative inverses for square matrices because otherwise the dimensions don't always line up. If you get to higher maths, there are ideas of inverse matrices for rectangular ones, but those are much more complicated and involve a lot more mathematics. So we're not going to talk about them yet. In fact, I'm not sure. We might talk about them a little bit in this class, but not very much. So now, if A has an inverse, we're going to call it invertible or non-singular. This is just terminology. This is standard terminology in the field. Invertible makes sense. Non-singular is a little bit weirder, but it means the same thing. And if A does not have an inverse, then it's non-invertible or it's singular. Now, there's a very important theorem, and we're not going to prove it in this class, though you would in some of the more theoretical linear algebra classes, that if you have a square matrix, the right inverse and the left inverse are the same. So this is important because if you remember matrix multiplication, if you swap the order of the multiplication, you actually don't always get the same result. This is a theorem that says that if you have square matrices and you look at the inverse, you can swap that order and you still get I. And so basically what we're saying is, let me draw this in red. And of course you still have this nice property of undoing if you multiply on the correct side. So A inverse AB is equal to A inverse A. You can't swap the sides, but you can like change the order in which you like combine things. A inverse AB, that's equal to IB, which is equal to B. And this I is the identity matrix. And similarly, BA, A inverse is going to be equal to B times AA inverse. Doesn't need that parentheses. Which is equal to BI, which is equal to B. So these are all for square matrices. And let's give a concrete example of this. So let's start with, let's do the one that we talked about earlier. So we know that minus 1, 1/2, 3/4, minus 1/4, we know that undid the operation of 2, 4, 6, 8. So we think that it ought to be the inverse. So if you multiply these together, what you end up getting is minus 2 plus 3, minus 4 plus 4, 3 halves minus 3 halves, and 3 minus 2, which is equal to 1, 0, 0, 1, the identity matrix, which is good. Now it turns out that this also happens to be equal to, and you should check this, 2, 4, 6, 8 multiplied by minus 1, 1/2, 3/4, and minus 1/4 in the opposite order. So a matrix has a single multiplicative inverse, and if you multiply on the left or right, you get the identity either way. So now, at this point, I've given you this idea that you can divide, so to speak, by a matrix by just finding the matrix inverse. But now, of course, the question is, how do you find it? Well, one way you can do that is you can solve a system of equations. So let's go here. So you might want to solve a system of equations. So this would be, so if you have 2, 4, 6, 8, well, we have some other matrix you want to multiply it by. So let's say this is x, y, z, w. So these are unknowns that we're solving for. And we want this to be equal to 1, 0, 0, 1. Okay, easy enough, right? So it's some matrix that when you multiply by it, gives you the identity matrix. And of course, we can expand these out by just using matrix multiplication. So this gives you 2x plus 4y here, because you take the first row and times the first column. And then you get 2z plus 4w, since you want the, well, first row times the second column. And you get 6x plus 8y, and 6z plus 8w. For the entries of multiplying these two matrices together, and we want to set this equal to 1, 0, 0, 1. But now, of course, in order for two matrices to be the same, all their entries have to be the same. Therefore, you get a couple of systems of equations. So one of them here, or you get a couple of equations, which we're going to organize into systems. So one of them here is 2x plus 4y is equal to 1. And you also get 6x plus 8y is equal to 0. And 2z plus 4w is equal to 0. And 6z plus 8w is equal to 1. Now, you'll notice, of course, that when you're doing this, you can, the left two equations only have x and y, and the right two equations only have z and w, so you can organize this into two different systems of equations. So you have this system with x and y, and you have this system with z and w. Now, of course, we know how to solve these, and one of the ways you can solve these is by using an augmented matrix and doing row reduction. So you get 2, 4, 6, 8, 1, 0, and another augmented matrix, 2, 4, 6, 8, 0, 1. But now, you'll notice that, of course, the first part of this augmented matrix happens to be the same because this is your 2, 4, 6, 8 matrix. And it turns out that you can, for notational simplicity, you can combine these into a single big augmented system, 2, 6, 4, 6, 8, 1, 0, 0, 1. So you can combine these together. Can combine both augmented systems. Okay, and now that once we've done this, we know how to solve an augmented system. So let's see. Let's go ahead and solve this using matrix operations. So this is 2, 4, 6, 8, 1, 0, 0, 1. And let's the first thing I'm going to do is I'm going to divide to make these things all ones because I prefer that. So let's say that R1 is going to be 1/2 of R1. So we're going to multiply by 1/2. So you're allowed to do this. This is going to be 1, 2, 1/2, 0. Now, I'm going to save some writing space. This is a little bit dangerous, but I'm going to do two operations at once. So you should be really careful when you're doing this, because if you do this wrong, you can actually mess things up. But I'm going to do this because each of the rows doesn't matter, and so I'm going to multiply the second row by 1/6. So let me just put this in red. Be very careful doing two steps at once. Because sometimes, because you can mess things up. So basically, you need to make sure if you're doing two steps at once that it would be the same thing if you did each step individually. But let's go ahead and do that. And so this is 1. This is going to be 4/3, 0, 1/6. Okay, so now let's now that we have this, let's subtract let's subtract 3 rows. And so let's see, I'm going to say that R2 is going to be R1 minus R2. And so then that's going to be not R1 is not going to change, but R2 is going to change. It's going to be 0, and that's going to be 2/3. And this is going to be 1/2 and minus 1/6. Now I'm going to divide the second row again. So R2 is going to be 3/2 times R2. So it's going to be, the first row again doesn't change, 1, 2, 1/2, 0. Second row is now 0, 1, 3/4, and minus 1/4. Okay, and our last step is, of course, we want to convert. We want to completely solve everything, so we're going to do a full Gauss-Jordan elimination, Gauss-Jordan reduction. And we're going to end up taking R1 is going to be R1 minus 2R2. And when we do that, you end up getting 1, 0, 0, 1 on the left here, and you get minus 1, 1/2, 3/4, minus 1/4 over here. And so this is one way of computing the matrix inverse. So this implies that 2, 4, 6, 8 inverse is equal to minus 1, 1/2, 3/4, and minus 1/4. Okay, any questions so far? So I know we've gone through a lot of steps. So basically the idea is, well, you can solve for the matrix inverse just by solving two systems of equations, and you can combine those into one big augmented matrix to do it all at once. And so let's go ahead and formalize that. So it turns out that this doesn't just work for a 2x2 matrix, it works for any n by n matrix, so any square matrix. If you can row reduce the augmented matrix where you put A on one side and the identity matrix on the other side, to the form where you have the identity matrix on the left instead of the right, then A inverse is equal to B. And if you can't do that, then the matrix doesn't have an inverse. So let me give a couple more examples. I'm going to give a couple of simple examples, just maybe the one that isn't quite that hard, since I'm going to do a 3x3. So let's suppose we had 1, 1, 1, 0, 1, 1, 0, 0, 1. If we want to find the inverse of that, we want to convert it to let's see, so we have the identity on the other side. And we want to convert the left side to the identity. Well, I chose an easy to work with matrix, so that I wouldn't have to write too much. And when you do this, I'm going to do two operations once again. So let's say R1 is equal to R1 minus R3, and R2 is equal to R2 minus R3. So what you end up getting is 1, 1, 0, 0, 1, 0, 0, 0, 1, and 1, 0, minus 1, 0, 1, minus 1, 0, 0, 1. And let's do it again. So then we need to subtract out. So R1 is going to be R1 minus R2 now. And so then you end up with 1, 0, 0, 0, 1, 0, 0, 0, 1, and 1, minus 1, 0, 0, 1, minus 1, and 0, 0, 1. And so now you know that this thing here, that is the matrix inverse. And you can double check by multiplying them back out, but we know that that is now the matrix inverse. Let me go ahead and give an example where this fails, though. Let's suppose we start with 1, 1, 2, 2 as our matrix. So we want to use the augmented matrix where we have the identity on the right side, 0, 1, 0, 0, 1. And what you'll notice is that in our first step, we take R2 is equal to R2 minus 2R1. And you end up with 1, 1, 1, 0, because the first row doesn't change, and 0, 0, minus 2, 1. Now, unfortunately, because we can't row reduce this down to the identity, so like it fails because there are two zeros there, what we conclude is that 1, 1, 2, 2 has no inverse. Okay, so now we've gone through a lot of techniques here, so it's a big algorithm which you should learn. And now let's have you all try it out. And let's go back to our rabbit example. So remember that we used to have a Leslie model, this Leslie matrix for rabbit population model. how do you find the inverse, the multiplicative inverse of L? So let's have you all do that now. So you need to solve for the this augmented matrix. So you need to solve for 2, 3, 0.5, 0.9, 1, 0, 0, 1, and you want to make this the identity. Let me reset the chat so that we can see everyone's votes, but let's see what people think. Of course, normally you don't necessarily get a multiple choice question, but when you do get a multiple choice question, there are actually two different ways for you to find the identity here. One is to solve this augmented matrix using Gauss-Jordan elimination, but the other way is you could just multiply them together and see like which one, like when multiplied with L, gives you the identity. So both of those are valid ways, assuming it's multiple choice, but you should of course also practice with the actually using Gaussian elimination, because otherwise you won't be able to solve it when I don't give you possible answers. And I will give you a couple moments here, and I'll just talk about why this is important. Well, remember, the entire idea behind doing this is that we want to, we often at times have an equation, something like LP is equal to, LX is equal to Y. And you want to solve for X when you already know what Y is. Now, if you have the multiplicative inverse, instead of having to solve the system of equations, all you have to do is you have to multiply both sides by L. And by both sides by L inverse. And so on the next slide, what we'll be doing is we'll be using the multiplicative inverse that we find here to directly solve for the previous year's population without having to solve another system of equations, but just by multiplying by a matrix. And so this is the power of matrix inverses. If you have them, you can undo the operation of a matrix multiplication without needing to solve another set of equations. It's just the multiplication operation. Okay, so we're starting to get some answers coming in. So let's see, we have an E, so none of the above. We have a couple B's, it looks like. Okay, so it looks like most people were able to get B for that. Okay, well, I'm not going to go do the full step of solving it because that'll take a bit too long right now, but what I'm going to do is instead I'm just going to check it. So 2, 3, 0.5, 0.9. And, well, let's see, people chose B, so that's 3 minus 10 minus 5/3 and 20 over 3. When you multiply this out, well, the first entry is 6 minus 5. So that's equal to 1, so that's a good sign. And the next entry is minus 20 plus 20. Oh, that's equal to 0. That's also a good sign. And this is 1.5 minus 4.5 over 3, which is also 0. And minus 5 plus 6. So this is equal to 1001. So yes, that is correct. Okay, so that's how we solve for matrix inverses. And for a 3×3 matrix, you do the same thing. It just might take you longer because, well, you have a bigger matrix. Now, the important thing is, once we have these things, we can solve linear systems using inverses. As I was saying a moment ago, can you please go through it? Yeah, so what we're doing here is we just multiplied through to check the different steps. If you wanted to actually go through all the steps of doing this row reduction, what you'd first do is step 1 would probably be row 2 is equal to, step 1 would be row 1 is equal to 1/2 of row 1. Step 2 would be row 2 is equal to row 2 minus 1/2 of the new row 1. And then after that, then step 3, normalize row 2 to get 1, and so on. So these are the first couple steps, and hopefully that's enough to get you started. in your tutorial on next Wednesday, we'll go. I'll ask your TAs to go through more examples of this. Oh, so let me be a bit more clear. Multiply to get leading 1. Because you want the leftmost entry to always be a 1, right? And so after you've subtracted out to send one of the entries to 0, you want to then multiply the entire row to get the entry to be equal to 1. And then once you have that, you can do back substitution. So this will require practice. There are practice problems in the book, and we will cover this more in the during your tutorials next week. And I'll stick around for office hours after if you want me to go through it again then. But for now, we do need, let's see. Well, let's see how we can use these. So we can solve these systems so we can solve a linear system by just multiplying by the inverse if it exists. And the reason for that is because, well, inverses undo the operation of multiplying. And so if you have a Leslie matrix, L is equal to 2, 3, 0.5, 0.9, and the population vector 230 is 59 in year 2, we can compute the population vector in year 1 by just multiplying. So this means that population in year 1 is going to be equal to the inverse of 2, 3, 0.5, 0.9 times 230, 59, since that's P2. And this is going to be equal to, well, we calculated the inverse a moment ago, minus 3, 10, minus 5/3, and 20 over 3 times 230 over 59. So that's equal to, with a little bit of multiplication, that's 3 times 230 is 690 minus 590. And down here on the bottom you have minus 1150 over 3 plus that would be 1180 over 3. So the math gets a little bit hairy, but this ends up giving you 110, which was the population vector in year 1. So once you have the matrix inverse, you can solve these systems of equations by just multiplying, which is why this is super powerful. Okay, so having gone through all these algorithmics, which we'll be covering again in tutorial, let's take a step back and think about what it means intuitively to have a matrix inverse. So now, you should recall that matrices are transformations of vectors. So for example, I had the super simple example 2, 0, 0, 2, where when you multiply by xy, that's equal to 2x and 2y. So one way of visualizing this is you can think of this as transforming a figure in the plane. So I'm going to transform the unit box this time, since this will turn out to be quite helpful. So let's say we have a unit box here, where this point here is going to be 1, 0, and this point here is going to be 0, 1. Then what this transformation does is it moves everything outward, right? So you end up getting, well, that goes to 2, 0 after this transformation, and this goes to 0, 2 after the transformation. And you end up with a bigger box, actually. So you end up with, let's use orange for this. You end up with a bigger box after the transformation. So the operation of this matrix was to make things bigger. So a matrix has an inverse when you can reverse the transformation. So now, of course, this was a simple matrix, and so the transformation was making it bigger. Well, does this matrix have an inverse? Yes, you just make everything, shrink everything again. And so it turns out, and this is something you can solve. This is actually not too hard to do, but the inverse of 2, 0, 0, 2 is just 1/2, 0, 0, 1/2. So the previous matrix expanded everything by 2. This matrix shrinks everything by a factor of 2 because you're multiplying by 1/2. And so you start with this big box, and it shrinks down to this small box. Okay, so long as you have this sort of continuous transformation, you can expand things, you can shrink them, and often you can reverse these transformations. But now, if a matrix sends 2 points to the same point, then you can't reverse the mapping, right? So let's give an example of that. So 1, 1, 1, 1 times xy is equal to x plus y, x plus y. But unfortunately, one of the things you might notice is that if you start off with this box, the small box here, and again, we start off with our two basic points as 1, 0, and 0, 1. This operation, well, where does 0, 1 go? 0, 1 goes to 1, 1. But we also have 1, 0 that also goes to 1, 1. Because, let's see, this was 1, 0, and this was 0, 1. So they both go to the same point. And in fact, this operation, what this does is it actually collapses this 2D figure into a line. In fact, collapses it into lat line, because that's the x plus y line. Wait, did I do that right? Yeah. So what that does is it collapses everything. And unfortunately, what that means is that both of these 2 points go to the same point here. And so you can't actually reverse this. So this matrix isn't invertible because you can't reverse this mapping. And in fact, if you take a look at the trying to solve for the inverse, you'll quickly find that, oh yeah, so basically if you apply this to every one of these points, you can look to see where they go, right? So I did it for this one point, 0, 1, and 1, 0, and both of those points get pushed in. And if you look at all different possible points, so if you think about using x and y, for any possible set of x and y, when you multiply, you end up getting, by that matrix, you end up getting this x plus y, right? So this means that no matter what point you start with, after you apply this transformation, both of the coordinates lie on the line where x is equal to y. Because your two coordinates are equal to each other, and so those all lie on this diagonal line. Does that make a bit more sense? So basically, this operation forces everything to collapse down to the line, even if they started farther away. So no matter where you start, you end up on this y equals x line after this transformation. But now this is a bad thing because you can't reverse it, and we can actually formalize these ideas of the collapsing into a line. And one way to think about this is to think about the different dimensionality and how matrices affect scaling. So this is a bit sort of a complicated concept, but let's start with a couple easy examples. So when a matrix, so let's start with a 1-by-1 matrix. So these are easy because these are the scalars, right? So let's suppose we have a matrix 2, and that operates on some vector x. Well, that's going to give you 2x, because this is a 1-by-1 matrix, and so when you have 1-by-1 matrices, you can actually just multiply them normally. And so if you start with a point on the line, so let's say we had a point here, which had value 1, well, that's going to go to a point here, which has value 2. And now this is reversible, right? Because you've scaled everything up by 2, and you can shrink everything down by 2. And so if you think about the length of this line, the line that corresponds to that vector is length 1. So if you take that line and you scale it, you end up getting a new line, which is length 2. Okay, so you go from a length 1 line to a length 2 line. But now, on the other hand, if you had the 0 matrix, then you actually end up with, oh, sorry, that's the next, oh, go away. If you have the 0 matrix, what's going to end up happening is no matter where you start, every single point goes to 0. How do you get the length 1 line? I just chose a length 1 line. So that was what I decided to start out with. So I started with a length 1 line, and then I asked what happens to that line when you apply this transformation. You could start with a length 2 line if you wanted to, but the idea is just that you want to start with some shape, and you're applying a transformation to that shape, because matrices apply transformations. Okay. So now that was a 1-by-1 matrix, and you can think of 1-by-1 matrices as operating on lines, on the real line. But 2-by-2 matrices, well, we had some examples of those. You can think of those as operating on figures in the plane. And so I'm going to operate on a square because squares are easy to draw and they have some nice properties. So let's suppose that we had a comparable matrix 2 0 0 2, and we want to apply it to a square. So this means that if you start with a small square here, for every one of the points in the square, we're going to multiply both of their coordinates by 2. Now note that this has area 1, and once you double this, you double both of the coordinates, the area of this new square is now area 4. And so, in some ways, somehow this matrix is still scaling your thing, but it's scaling it by 4. So like, if you start with something with area 1, it's now going to have area 4. So you start with a 1 by 1 box, you end up with a 2 by 2 box, which has area 4. But now let's think about what happens when you apply a different matrix. This matrix here, 1 1 1 1, which we know is not invertible. So xy, that's equal to x plus y, x plus y. So everything that so after this operation, everything ends up on this line where the two coordinates are the same. So if you do this, what you end up with is you have this square to start out with. And if you apply this matrix to every single one of the points in the square, which is admittedly a little bit hard because you have to do it for every point, but what happens when you do this is you end up with this line here. And what's the area of a line? Well, the area of a line is 0. So you start with area 1, and you end up with area 0 because a line has no area. And so what this has done is you've taken this 1 1 1 1 matrix has squashed something that has area into something without area because it's just a thin line. And the same sort of thing happens in higher dimensions, though it gets harder and harder to visualize. So when a matrix squashes a 3D cube to a 2D plane, that's also irreversible. So note that a cube has non-zero volume, but a flat shape has volume 0. And let's give an example of that. I'm going to choose a simpler example because these are hard to draw. So let's say 1 0 0 0 1 0 0 0 0. When you multiply that by a 3 coordinate, a coordinate in 3 space, you get x, y, z. So that's equal to x, y, 0. And so what ends up happening is you start off with a cube of volume 1. So if you start with a cube of volume 1, that's going to go to just a flat plane. So you've squashed everything down because you've gotten rid of the z-axis, and that has volume 0. Okay, so somehow we want to link this sort of squashing down dimensions. So our original figure, a line is 1-dimensional, a point is 0-dimensional. A square is 2-dimensional, a line is 1-dimensional. And a cube is 3-dimensional, but a flat plane, or a square, is 2-dimensional. And so when you reduce the dimensionality of a shape, you end up reducing the volume or the area or the appropriate length. So whatever the highest dimensional type of area is, to 0. And that sort of squashing is irreversible. And that's sort of the point we're trying to convey here. Now, you might wonder, how do you come up with these areas? How can you measure them? And that's a little bit difficult, but it turns out there's a really powerful mathematical tool that people have developed that formalizes this idea of scaling of areas and volumes. And this is something called a matrix determinant, which you might have heard of before, and there are some nice formulas for it, but these formulas actually have this interpretation of area or length or volume, or they're a scaling behavior. So the determinant of a 1 by 1 matrix is just whatever entry was in there. The determinant of a 2 by 2 matrix is a little bit more complicated. It's actually AD minus BC. So the two things on the main diagonal and the two things on the opposite diagonal subtracted from each other after multiplication. Very important note, even though this notation, these bars, look like absolute values, they're not absolute values, and determinants can be either positive or negative. So if we go ahead and give an example here, so I'm going to write this bar around a matrix because otherwise it's not obvious that this is a matrix. So this is just to distinguish the determinant from an absolute value. The determinant of the minus 1 by 1 matrix is just minus 1. The determinant of the 1, 2, sorry, that's a 2, not a 1. 1, 2, 3, 4 matrix, that's going to be equal to, well, we're first going to take the 1 and the 4 here. So that's going to be 1 times 4. And we're going to subtract from that the product of the 2 and the 3 here. So 2 times 3. So this is equal to 4 minus 6, which is equal to minus 2. And lastly, the determinant of 1, 1, 1, 1 is equal to 1 minus 1, which is equal to 0. So the determinant, you remember how we talked about the scaling behavior on the previous slide? The determinant represents the scaling behavior of what happens to a unit box, or unit line, or unit volume, or unit cube, depending on what dimension you're in. So if you're using a 2 by 2 matrix, the determinant represents the volume scaling of a unit square. If you're in 3 dimensions, then it represents the the area scaling of a unit square. If you're in 3 dimensions, it represents the volume scaling of a unit cube. So this is, there are actually many different interpretations of the determinant. This is one of them that I think is the most geometrically intuitive. It is how the volume of a shape scales. In fact, if you take a look at this determinant of this 2 by 2 matrix, for example, so if you were to take the determinant of 2, 0, 0, 2, that's equal to 4. So that actually is the same as this volume scaling that we just described. Okay, hopefully that answers that question. Now, I want you guys to try this out because you guys need to be able to take determinants. So, oh, wait, what just happened? There. So let me reset the reset this. And so yeah, what is the determinant of this figure? Okay, so we have a lot of pretty immediate replies. Looks like people agree that this is C. Yep. Okay, so why is that? Because this is equal to, well, 0 times 0 minus 1 times 2, which is equal to 2. Okay. Let's do another one. So let's do that one. What is the determinant of this? And I'm going to reset just so that we can start counting again. Yeah, so what is this equal to? This is 1 minus 1 times minus 1, which is equal to, looks like everyone's been getting this. So this is equal to, well, 1 minus 1 is 0. Okay, good. So, taking determinants of 2 by 2 matrices isn't that hard. And now let's bring this to the punchline, which is that determinants are equal to a signed scaling factor. So determinants can be negative. But remember, when we were talking about areas in with integration, sometimes we had a positive area and sometimes we had a negative area, right? So determinants have the same sort of behavior. And, oh, wait, what just happened? Oh, sorry, I need to draw on this. Yep. So in 1D, so because this is easier to understand, when you have, say, 2 times x, this is equal to 2x. And what this means is that if you have a line of length 1, so we're going to start with a line of length 1 just because it's easier to understand. So if you start with a line of length 1, that's going to turn into a line of length 2. So because you're scaling things up by a factor of 2. On the other hand, if you had, say, minus 1x, that's equal to minus x, well, this doesn't actually, the determinant of that is actually just minus 1. And so instead of scaling it up by 1, what's going to happen is you're going to actually flip it. So if you have a line there, the new line is going to be there. And so the minus sign actually represents somehow flipping across, some sort of flipping transformation. We're not going to go into too much detail there, but this is why you have negative scalings, because when you have a negative scaling, that means you flipped something. In 2D, it's a little bit harder to interpret. So in 2D, but we're going to take a little bit of time to do that since I think that's important. You have A, B, C, D. xy is equal to ax plus by cx plus dy. So this is obviously harder to interpret. But one way to do that is to think about what we do to the unit square. So note that a, b, c, d times 1, 0 is equal to ac, and A, B, C, D times 0, 1 is equal to BD. And what that means is, note that those two coordinates are precisely the two n coordinates of this unit square. So this coordinate here is 1, 0, and this coordinate here is 0, 1. And of course, you can just add these things together. So this coordinate here happens to be 1, 1. But what's important here is that we know where these things go under the transformation. So where these things are going to go is you're going to have a shape that looks like this. Because this coordinate here is AC, wherever that is, that coordinate is going to be BD. And if you want the 1, 1 coordinate, you just add them together, so you can compute that as well. So that coordinate is going to be AC plus BD. And you can double check that the 1, 1 coordinate does actually go there. And so what we've done is we've transformed this square into a parallelogram. And now we want to find the area of this parallelogram. So there is a nice visual interpretation that I was looking for last night because I was trying to find a good visual proof of this determinant being equal to area. And so let's suppose we draw our parallelogram this way. So note that our coordinates AC and BD are still at the correct points on this. And I've just drawn out diagonal and vertical and horizontal lines corresponding to these different points. Now this is the same parallelogram we were looking at before, and what we're going to do is we're going to match together different areas and try to convert this into an easier to understand shape. So note that the blue part up top here is the same as the blue part down there, which is outside of the parallelogram. And so what we're going to do is we're going to move all the stuff from up top. So we're going to move this area down to here, and we're going to move this area over to there. Okay, and it shouldn't take that much work, but you can convince yourself that those triangles are the exact same size, so you're not actually changing the area. And so you end up with this shape here. Well, now the next thing we're going to do is we're going to do the same thing. So let me convert all those line colors to purple. And what we're going to do is we're going to do the same thing with this bottom left corner here. So we're going to take this blue section and move it up here, and this green section and move it over here. And once we've done that, what you're left with is this parallelogram shape where you've cut out this corner in the bottom left. And now it's easy to compute the area because the area is just the big rectangle minus the small rectangle. So it's AD minus BC, which is precisely the formula for the determinant we had earlier. And so this is sort of explaining why when we do this determinant, you end up getting the shape of appropriate shape, parallelogram's area. Okay? And so basically what the determinant represents is this sort of scaling. And if you ever scale the determinant down to 0, then what happens is, or if the determinant scales the area down to 0, then that means you're collapsing things onto a line. Because something that has area 0 is not two-dimensional anymore, it's now one-dimensional. Or if you scale a cube onto a plane or a line, then it no longer has volume anymore. And so let me end with a couple important properties of determinants. So basically, come on. So a square matrix is invertible if and only if its determinant is non-zero. So this sort of makes sense intuitively because if a matrix squashes away a dimension, then it's not invertible and vice versa. So again, we had 1, 1, 1, 1 is equal to 1 minus 1 is equal to 0. The determinant of that is equal to 0, so not invertible. So this means that the determinant gives you an easy test to know if something's invertible without having to go through the entire process of Gauss-Jordan elimination to try to find the inverse. Alternately, we also have that if A is a square matrix and A of x is equal to 0 for some non-zero vector. So if it squashes some non-zero vector to 0, then it's also not invertible. So in this particular, sometimes this is easier, sometimes this is harder. But in this case, 1, 1, 1, 1, if we multiply it by 1 minus 1, this turns out to be equal to, this is equal to the 0 vector, which is an important distinction to make, because when it's clear, we're going to use 0 to represent the 0 vector. It won't always be clear, but hopefully it will be. generally, so not invertible, because it sends some non-zero vector to 0. And lastly, let's end with, I'm almost out of time. Let's end with determinants and matrix multiplication. So if you think about it, matrices are just transformations, and determinants are assigned area. So if you do two different transformations, you can just multiply together the determinants to get the scaling behavior of the combined transformation. And so therefore, determinant of AB is equal to the determinant of A times the determinant of B, assuming, of course, that A and B are the appropriate sizes. So, for example, 1, 1, 0, 1 and 2, 0, 1, 2. If you multiply these together, that's 3, 2, 1, 2. And if you look at each of the determinants, the determinant of 1, 1, 0, 1 is equal to 1. The determinant of 2, 0, 1, 2 is equal to 4. And the determinant of 3, 2, 1, 2 is equal to 6 minus 2, which is equal to 4. And 1 times 4 is equal to 4. And so one of the other cool things about determinants is you can multiply, if you multiply together matrices, you also multiply together their determinants. And I think I will stop here since I'm out of time. When we come back when we come back on Friday, we're going to talk about higher order determinants. So it turns out that you can actually take determinants of bigger matrices, we just haven't defined it yet. And we're going to talk about that a little bit before moving on to eigenvectors and eigenvalues. But let's end here, and I will see you on Friday.